Hello everyone, once again welcome back to the series of problem solving sessions from design. In this video also we'll be solving a simple problem from the concept of combined loading and principal stresses, which is similar to the last one that we have discussed in the previous video. But here the combination of three different loads, that means the axial force, the bending moment, the load which causes bending moment, and also a torque are acting on this shaft. And also another difference is this shaft is hollow, that means it is having an inner diameter of 25 mm and an outer diameter of 40 mm. And the load values, that is the three values, axial force here also you can visualize in here 9806 Newton, twisting moment of 180 Newton meter, but here it is given as kilonewton, actual value is Newton meter, 180 Newton meter, and a bending moment. So here only the magnitude of bending moment, if some transverse force is acting, then this will be creating a bending moment, and that maximum magnitude of bending moment is given 79 Newton meter. So for this loading we have to evaluate the where the critical point is located, and for that point we need to evaluate the stresses, principal stresses. So if you're observing, this will be creating, this axial force will be creating axial normal stress sigma A. This torque will be creating torsional shear stress to suffix T. Both of these components we have seen in the previous video. Here this bending moment will be causing normal bending stress sigma B, or flexural bending stress or flexural normal stress sigma B. So all these components we have to evaluate at the critical point, then we have to find the principal stresses. So for this sigma A, this is critical at all sections and at all points that we have seen in the previous video. And this tau T, here torque is applied at this section, which will be transmitted uniform at all sections, but the magnitude will be maximum at the outer surface event, that also we have seen. And here bending moment value is given, that means the bending moment is also uniform, that means at all sections, but bending moment will be maximum at which location, that we need to find. So you are already knowing the other things we have seen in the previous video. Here I am explaining for the bending moment only. So bending normal stress sigma B, you are having m by I into y. So this sigma B is becoming maximum when this y is becoming maximum. That occurs, y is the distance measured from the neutral axis. So for this figure you can call this as the neutral axis. You have studied all these things in MOS. And this y is measured from this neutral axis, and wherever y is maximum, that is at this point or this point. So here this side will be the tension side and this will be the compression side. Based on that you can put plus or minus sign for tension and compression. So if you are drawing the variation at this location, maximum tensile stress will be coming, and at this location maximum compressive stress will be coming, and this will be the variation where along the neutral axis there will be zero bending stress. If you are combining the effect of axial load, the shear load, and the bending load, the critical element will be lying at this point, because this is coming, this the topmost point. And for torque, this is actually all the outer surface elements are critical. And here for the axial load, all elements are critical. And here for sigma B, top and bottom elements are critical. So by combining all these three cases, all elements, outer surface elements and top or bottom elements, we can take the critical elements at this point. I will be taking only top because this sigma A will be creating a tensile stress. This will be tensile, and the sigma B will be at this side, or the top side is tensile and the bottom side is compressive. So here the sigma A will be acting in this direction and sigma B will be acting in this direction. So both will be getting added up. So that point will be the critical element, and I will be drawing the critical element here. Then I can mark the stress component sigma A due to axial load and sigma B, that is due to bending. Both will be getting added up in this direction. Then we are having the shear stress component, which is in this direction due to the torque applied, that is complementary is also in this direction. So this is tau suffix t. So these three components will be here: sigma A, sigma B, and tau suffix t or tau t, torsional shear stress. We can use the same equations from this data book. So all these equations are given. The axial normal stress, force by area, bending stress is this one general. But here we'll be making use of this simple expression because here the shaft is hollow. So you cannot substitute IS directly because this is given for a solid shaft, this case bending. And similarly for this torque equation is given for corresponding to this figure is also given for a solid shaft, but here we are having a hollow shaft, and that I will be discussing how to take those values. Once you are knowing these components, then we will be applying based on this state of stress. That means based on this state of stress we can find the principal stresses using the maximum and minimum principal stress equation. So for these three loads I will be finding the components of stresses. So this creates an axial normal stress sigma A, which is, if I am taking this as the critical point, this is our critical point, or the critically loaded point is located at this one, and at that position sigma A value is equal to force by area. This force is 9806 Newton divided by area. Here we are having an outer diameter of 40 mm and an inner diameter of 25 mm. So we have to evaluate the area based on that. So this will be equal to pi by 4 into d outer square minus d inner square. This is d outer square minus d inner square. We need to substitute those values. So it is 9806 divided by pi by 4 into, here I will be substituting in meters. 40 mm is 0.04 meters minus 25 mm is 0.025 square. So I can simplify this and you will be getting this value as 12.81 into 10 raised to 6 Newton per meter square. This is equivalent to 12.81 megapascal. So this is the value of axial normal stress due to the force 9806 Newton. Next we will be evaluating the effect of next load. Here we are having the bending moment. This is actually the bending moment, and this is the force, and this is the torque. So due to this bending moment, I already mentioned bending stress, bending normal stress will be occurring, and here I will be writing the general expression, which is m by I into y. Here we are finding this for this critical element, which is located at the outer surface, that is at a maximum distance from the neutral axis. So for finding that one, this y to be max, then only we will be getting the maximum value of this bending. In that case we need to solve for, and here the m value is given. The bending moment is equal to 79 Newton meters SI units. I value we need to substitute or find. So this I is for a hollow, for a solid shaft it is pi d raised to 4 by 64, but a hollow shaft it is pi 464 into d outer square minus d inner raised to 4 minus d inner raised to 4. And y max I mentioned, it is the maximum distance from the neutral axis, that is to this fiber, and that will be equal to the radius of or the outer diameter by 2, that is do by 2. So here all values you can substitute in meters. Bending moment is 79 Newton meter, do is 0.04 meter, di is 0.025, and if you are substituting all these values, then you will be getting the sigma b max also in megapascal. The correct value to be obtained is 14.84 megapascal. Similarly, the effect of last load, that is this torque we will be taking. We are already knowing torque will be creating a torsional shear stress, and here also I will be using the general equation. Similar to this m by I bending moment, we are having the torsional moment torque, and I we are having the polar moment of inertia J, and this y max we are having the radial variable R max we need to take. So here I will be writing the similar equation for torsion. So tau T equal to, instead of m we are having T by J into R. and we need to evaluate for R max, which is again outer diameter by 2. So I'll be substituting torque value is 118 Newton meter SI value or SI units, and J value is pi by 32 into d outer raised to 4, d outer raised to 4 minus d inner raised to 4, and into R max is d outer by 2. Here also I will be substituting all these values. This outer is to be 0.04 meter and this inner is to be 0.025 meter. Then I will be getting the value of, this is actually bending, then this torsional shear stress value will be of 11.08 megapascal. So now we have evaluated the effect of all these loads, that is the axial load is creating axial normal stress of 12.81 megapascal, bending is creating, or the bending moment is creating a maximum bending stress which is tensile, because both this tensile will be getting added up. I have shown in that previous element, and the torque is producing a torsional shear, and that value is 11.08 megapascal. Next we will be drawing the state of stress, and from that state of stress we will be evaluating the required principal stresses and maximum shear stress. So this is our member subjected to the combined loads, and here we are having the critical element at the outer top surface element, and this element I have again redrawn to this space, and where this normal stress is actually the sum of sigma axial and sigma bending, because both are tensile, which gets added up, and that makes that point critical. And so the net stress along this x direction, I can call this as the sigma x direction. So sigma x will be sigma a plus sigma b, and that value is 12.81 plus 14.84, that will be getting up to 27.65 megapascal. And along the y direction there is no normal stress, so our sigma y is 0, and in that xy plane the torsional shear is tau xy, which is equal to the torsional shear stress tau t, and that value already we are having 11.08 megapascal. So we are having sigma x equal to 27.65 megapascal, sigma y equal to 0, and the torsional shear stress tau xy, in that xy plane it is 11.08 megapascal. So from this one we can evaluate the principal stresses. We are having the expression of principal stresses sigma 1 and sigma 2. If you are knowing this stress component, 2D state of stress component, sigma x, sigma y and tau xy, which is sigma x plus sigma y by 2, plus or minus, plus will be giving you sigma 1 and the minus value will be giving you the sigma 2 or the minimum principal stress. So all these values you can substitute in this one. Then you will be getting the maximum principal stress sigma 1 for this critical point as 31.54 megapascal. That is the answer, 31.54 megapascal, and sigma 2 is equal to minus 3.89 megapascal. These are the maximum and minimum principal stresses at the most critically loaded point, and from this one we can find the maximum shear stress from the concept of Mohr circle, if you are knowing. So again I am explaining, this is sigma 1, this is sigma 2, diameter is sigma 1 minus sigma 2 for this circle, and this will be the maximum shear stress tau max, which is actually the radius, that is sigma 1 minus sigma 2 by 2, or half of that difference, and that value will be getting as 17.71 megapascal, which is the maximum shear stress for the critically loaded point. So these are the things which are asked in the question, the principal stresses and the maximum shear stress at the critically loaded point. So again, thanks for watching and hope you understood.